All right, today the topic is momentum. And hopefully you recall momentum and its symbol, the P symbol for momentum, a vector quantity equal to the mass times the velocity with which it is moving. When Newton defined force, he in fact defined force in terms of momentum. That he said that force was the rate of change in momentum. We could write that better as, instead of force, the net force is equal to the instantaneous rate of the change in momentum. Momentum being mass times velocity. If you take the derivative of that with respect to time, hopefully mass is not changing with respect to time, and you end up with the derivative of velocity with respect to time, which is of course acceleration. But this relationship between force and momentum is the one that you will apply as you do this checkpoint. That if it is a momentum time graph, then the derivative of momentum with respect to time is of course the slope. And using that idea, you should be quite successful at both questions A and question B for this checkpoint. Please, of course, put those on your worksheet. In your book, there is a convention that they will use lowercase letters if they're talking about a particle, and capital letters if they're talking about a system of particles. And so we have the statement that if the net external force, forget the if, is equal to the rate of change in the system, and of course, if the net external force is zero, then the rate of change in the momentum of the system is zero. But if the rate of change in the momentum of the system is zero, then the momentum of the system is not zero, but it is constant. This is called conservation of linear momentum. That if there is no external force, then the momentum will not change. It will be conserved. The question arises, what about nonlinear momentum? And the meaning we give to nonlinear momentum would be rotational momentum or angular momentum. And of course, it also has its own law of conservation, which I'm sure you can imagine, but we won't go there now. And also, what about internal forces? But this, of course, takes us back to the discussion we had with center of mass, that the external forces caused acceleration of the center of mass, and what we would get if there is no net external force is there would be no acceleration, which would mean no change in velocity, and so no change in momentum. But the internal forces, just as was the case previously, are all going to come in action-reaction pairs, and they will add up to zero. So internal forces don't matter. External forces do. You may recall previous statements that linear momentum is conserved in closed, isolated systems, and you may or may not recall what the words closed and isolated mean, but isolated meant sort of removed from outside influences. That would be without any external forces acting. Closed means that no mass gets in or out. That's probably less of an issue, but please hold on to this fact that you will do problems where you're going to say, I want to use that momentum is conserved. And when you do, you will justify your stating that momentum is conserved by asserting that the net external force is zero. And you could even go further to say the net external force horizontally is zero, so that the horizontal momentum is conserved, but the net external force vertically might not be zero, and then the vertical momentum would not be conserved. But you would make that assertion as you set out to do a problem, saying, hey, I'm going to do this problem in terms of momentum being conserved, which I would indicate by saying the change in momentum is zero, or perhaps better, P1 is equal to P2. Momentum is a very powerful idea. It is conserved relativistically. It is conserved at the quantum mechanical level, unlike energy, which is not conserved mechanistically, not conserved relativistically, and neither is energy conserved quantum mechanically. And you might reflect on what you know about how they could not be conserved at those levels. So momentum, which is conserved to all realms of physics, becomes a very, very powerful principle upon which to do problems. In fact, the whole invention of neutrinos, and I believe also weak nuclear force, was because they were concerned about momentum being conserved, and so they had to invent these other things, which turn out to exist, to make sure that momentum was conserved. So again, as I've already said, that it's conserved component-wise is what I usually said in the past, that such as in a projectile's motion, you would have an external force in the y direction, and so the momentum would not be conserved in the y direction. But if there was no external force in the x direction, then momentum would be conserved in the x direction. And please pick up on that subtlety. I have here another checkpoint applying excuse me, the idea of momentum conservation. Please work through this and answer questions A and B on your worksheet. And finally, this problem, which I think is very rich, and I think is a prime example of the power of my subscript method for dealing with relative velocity. And I would ask you to suspend your disbelief that anything good could come out of relative velocity, and stay with me as we work through this problem. You have this hauler, which has a cargo module on the back, and it's moving along at this speed relative to, oh my, relative motion, relative to the sun. And then there's an explosive device which causes the cargo module, which has 2/10 of the total mass, to shoot away, to move not relative to the sun, but to move relative to the hauler at a speed. And they give those relative speeds, and they want to know how fast is the hauler then moving relative to the sun at the end. And I would suggest that this problem would start with the fact that momentum is conserved, and so you would state that the momentum at the beginning is the same as the momentum at the end, and that you have the right to state that because there are no external forces acting. I presume that we're moving relative to the sun, but the sun is not accelerating this cargo. It could be. And then we would have a little more work to do. And so the mass times the this is not a statement of momentum. This is a statement about the center of mass. The total mass times the center of mass is equal to the mass of the cargo module times its location plus the mass of the hauler times its location, and then I will differentiate this equation relative to time, and bingo, out pops this equation, which is very nice in terms of my conservation of momentum approach that I am taking. My picture is going to get messed up. At any rate, we have this statement here. Now, this should be over here. Sorry about that. So the initial mass, which was the total mass of the two, times the initial velocity, is equal to the mass of the hauler times its velocity, plus the mass of the cargo module times its velocity. All of these relative to the sun. But then I'm going to take this idea which I developed here, and I'm going to use the fact that the velocity of the hauler relative to the sun is equal to the velocity of the hauler relative to the module plus the velocity of the module relative to the sun. And thus this initial momentum equation that I had becomes this momentum equation, where the velocity of the module relative to the sun is replaced by, I have subtracted this quantity from that, is equal to the velocity of the module relative to the sun. Well, how sweet is that? Because I knew the initial velocity relative to the sun. They gave me that. I'm trying to find the velocity of the hauler relative to the sun. There again is that unknown quantity I'm trying to find. And they gave me the velocity of the hauler relative to the module. So I can plug in values and ultimately solve for VHS. And that is pretty cool, and I hope you feel so too. Thank you very much.